Hi and welcome. I made a video on the two envelopes paradox, and this is going to be the video on the solution, and I have a feeling that a lot of people aren't going to like this one because it's actually ridiculous, and I probably some people won't believe me at all. I think this is worse than Monty Hall's paradox. It's way worse in my opinion. So let me just quickly describe the two envelopes paradox again, but I'm not going to go into all the details that I went into the other one. I'm just going to summarize the facts so far. So, the way the game works is randomly from some probability distribution, we're going to put some amount in one envelope, and then we're going to put twice that amount in the other envelope, and then we're going to shuffle the two envelopes and present someone with them at random. We're going to give them one envelope at random, and they have to decide whether they want to switch envelopes or not. But they do get to look inside their envelope first. So say they look inside their envelope and they see X amount of dollars. Well, it could be that they got the one with the smaller amount, in which case the other envelope will have 2x dollars in it. Or it could be that they got the amount with the larger amount, in which case the other envelope's going to have X over $2 in it. Now you can find a probability distribution such that no matter how much money you see in your envelope, you're always going to gain money on average from switching. Now that probability distribution is 1 over 3 times 2 over 3 to the power n probability to put 2 to the n dollars in an envelope as the smaller amount for n equals 0 to infinity. But I'm not going to go over all the math. But it is true that, yeah, the expected value, if you switch here, you're going to have 2/5 probability to get the larger amount. So you have 2/5 probability to gain X dollars, and you'll have 3/5 probability to lose X over $2. So you're going to gain X over $10 on average by switching, no matter how much you see in your envelope, unless you see $1 in your envelope, in which case you're guaranteed to make $1 if you switch. So if you see $1, you should definitely switch because you're always going to gain. If you see more than $1, you should still switch because you're going to gain, X over 10 on average. So now let's talk about why this is so weird, okay? Because when you originally see the two envelopes and you haven't looked inside your envelope, you don't know anything. There's a symmetry in the problem. You have no information from which to judge this envelope to be any better or worse than this envelope. There's just nothing to go on. So, should you switch if you haven't looked inside? It doesn't matter if you switch or not, right? But now say you look inside. Okay, well now you should switch, because you'll always gain more on average by switching. That's what the math says. Okay, let's just go back to here real quick. Before you even looked inside your envelope, you already knew that no matter what you see inside your envelope, you're gonna want to switch. So someone might come along and say, why even bother looking inside it? I already know that no matter what I see inside it, I'm gonna want to switch. So you know what? I'm just not gonna look inside, and I'm just gonna switch. I'm gonna save myself the effort of even opening the thing. So, which is right, because according to that argument, no matter what I see inside, I'm gonna want to switch. So I'm just going to switch without looking inside. According to that argument, it does, switching is better, but there's a symmetry, so switching doesn't matter. So what's the solution? Well, first of all, and I think most people will agree with this, if you don't look inside your envelope, then it doesn't matter if you switch. It's as simple as symmetry. Okay? Good so far. Now, if you do look inside your envelope, it is true that no matter what you see inside your envelope, you're gonna want to switch because you're gonna gain on average. That part is also true. And the math argument is actually correct about that. So, what's the flawed principle? The flawed principle is this. The following claim is false. If, no matter what I observe, I'm gonna want to switch, then it's better to switch even if I don't observe. That principle is actually contradictory, at least for some kinds of probability distributions, for some types of you know, sort of probabilistic scenarios, that actually fails. And that's really kind of uncomfortable, because it feels like a very reasonable principle. It's essentially saying, if no matter what I see, one strategy is always going to be better, then that strategy should also be better even if I don't see anything, even if I don't look. But it fails. So let me know what you think, and let me know if you agree, first of all, or if you think something else has gone wrong. And by the way, this paradox does require unbounded potential prize amounts in order to work. So, you know, of course you can't do it in this universe, but I do think you could imagine an alternate kind of universe where there's sort of like infinite usable energy that's available, and it's stable in the right ways, and you have some kind of like random bit generator to do the probability stuff. And in that universe, you could almost always carry out the paradox in finite time, at least as far as I understand. So yeah, let me know what you think, and thanks for watching, and take care.